I think if we're both right here, it should be fine. Yeah, if you can do them. Unless, I guess if you want to be on that side or this side, doesn't matter
Yeah,
to me.
it's my laptop. Okay.
Yeah, it's your laptop. You touch it. I won't touch your laptop. Since my Linux laptop was unhappy with the conference Wi-Fi, his Mac is totally fine. So there we go.
It's the world's most powerful presenting a slideshow.
That's right. At our office in New York, there's literally a Mac Mini sitting over in the corner just playing Spotify to the Sonos speakers.
Yeah.
It's like, really? We're using a Mac Mini for this?
The world's most powerful speaker.
Yes.
Are we good? Are we good to start?
Are we time? Oh, yeah, we are time.
Yeah.
All right. Good morning, everybody. Welcome to what's probably your first talk at PyCon 24. So, good morning. My name's Kevin Fleming.
I'm Charlie Marsh.
We're going to talk to you today about things you can do to make the building and testing of your Python applications better for you and for the world. But before we dive into that, are any of you the kind of person who likes to have a copy of the slides for presentations that you see? If you are, get your phones out, open your camera applications or your barcode scanners, and point them at the screen now. Say when you're ready. Oh, they're ready.
Sorry.
All right. Who's got the slides already? Woohoo, I see hands up. Excellent. Just for because this is a talk sponsored by Fastly, and I work for Fastly, I will say that you just got the slides from Fastly. So there you go. All right, great. You've all got a copy of the slides. Excellent. Moving on. So, will you introduce yourself first? I was just talking.
Sure. Hey, I'm Charlie Marsh. I started a company called Astral. We build high-performance tooling for Python, largely written in Rust. So if you've heard of or used Ruff before, I'm the original author of Ruff. We also built a tool called UV, which is a sort of a pip alternative written in Rust. So I'm very interested in building fast software, and that's what a lot of this talk will be about.
Thank you. And I'm Kevin Fleming. I've been around the open source community for longer than I care to admit, but most relevant for this, when I was at Bloomberg and ran the open source program office there, I was one of the people that got Bloomberg first involved in sponsoring the PSF. If you go to the exhibit hall, I'm very happy to see they're still doing that and have a gigantic booth right in the middle of the exhibit floor, so that's a good thing to see. I now work at Fastly and manage our developer relations team, get to work with the fantastic Hannah Aubrey, who runs our Fast Forward program, which is how we support the PSF at Fastly. And then I am the creator of some small Python projects, a couple which are just Ansible modules, which don't really see much use, but another one which is called Ginginator, which is a CLI for rendering Jinja templates, which is now getting 40,000 downloads a month from PyPI, so I'm pretty happy about that. So if you've ever had a need to do that, check it out. There's a link in the slides. This is the jillion ways you can get right in touch with us if you feel like you need to.
I'm a little more minimal, I guess.
Yes. I didn't list all the IRC networks that I'm on and other stuff. So, yeah. So.
Yeah, well, if you have the slides, you have this information for later,
That's right.
too.
Yep. All right. So our goal here is to sort of make you aware that the choices that you make when you are choosing tools for your projects and how you build your projects and how you test your projects, they not only have benefits for you and the people that contribute to your projects, but they also benefit the rest of the world. Resource consumption, data center power usage, all of those kinds of things.
So what are we talking about? What are we talking about when we're talking about trying to save time and save resources, right? There's a couple different forms of time and ways that time and resources are used. So the first of those is end user time. So the end users of your software, the time that they are waiting for your software to run and complete.
Yeah, so one of the things we can do to make that better, of course, is to just write better software that does the work more efficiently and use better tools for that purpose, which you're going to hear more about here. In some cases, we can also make our software do work in parallel so that it makes the wall clock time, the time the user perceives, be lower, even though the same amount of computation time was spent. And then finally, and most importantly, and we're going to be harping on this a lot during this presentation, do less stuff. There are people who have said that the fastest code that ever runs is the code that never runs. So the more you can do to avoid doing work, the better off everybody is.
So the other form of time that you might think about is developer time. So this is the time that it takes you as the developer to, edit and test your change. So one sort of iteration loop of I need to do something and see the output net effect of it.
So, guess what? You can also use tools that work more efficiently, just like you can write your own software more efficiently. You can use tools that do work in parallel. And of course, you can use tools that do less work. All of these things you're going to see. We're going to kind of repetitive here on purpose.
The third form of time is contributor time. So when people are contributing to open source, there's a lot of different ways that they are spending their time when they get to your project. It's, how do I figure out how to run it? But then also, once I've made a change, what's the feedback loop like there? How long does it take for your CI to run? How long does it take for tests to run? What is the loop between when I start to contribute and actually get feedback on the work that I'm doing?
Yep. Anybody want to guess what 3 things we're going to tell you can do there? Guess what? You can have CI do work more efficiently. You can have it do work in parallel. And of course, you can have it do less work.
And the final form of consumption and time that we're thinking about here is actually resource consumption. You can make something faster by parallelizing it over like a million machines, but you're then consuming more compute, more resources. So there are some trade-offs there around how do you write really efficient software that's also efficient in terms of the resources that it consumes.
Yep. And we're going to have the same 3 things again, but with a caveat. First, of course, is using better tools that work more efficiently is going to reduce resource consumption. That's good. Doing the work in parallel, though, isn't always a saving in resources, and we'll talk a lot more about that later in the talk, but that's something you have to be really careful about. And then obviously, doing less work means using fewer resources. So that's a big win. All right, so the first part we talked about, making your software more efficient for your users. Does anybody here who writes software for people want them to have to spend more time using your software? I hope the answer is no. If the answer is yes, you have a very strange personality. But yes, our software should help the people who use it get their work done in less time, and we want to achieve that. So, a couple of things you can do there. How many of you are running software in production on a long-term support Linux distribution that was not released this year? Not very many hands.
Probably me.
Okay, not very many hands. I expected more. I think that's probably good. One of the best things you can do if you are forced, I guess, maybe the way to choose, if you have no other choice, don't use the version of Python that's provided by that version of that LTS Linux distribution. Because they are long-term support distributions, they're going to stick with whatever version they had when the first version of that was released. And they'll apply bug fixes and lots of other things to it, but you won't benefit from the performance improvements that happen when new versions of Python are released every year. And in particular, looking at the time period between 3.8 and 3.12 and now 3.13, which just went into beta last week, I believe, there's been gigantic performance improvements. I saw benchmarks from 3.10 to 3.11, I think, that across the core benchmark suite. 25% performance improvement just by switching from Python 3.10 to 3.11. So those are things that you can choose to do when you're deploying your software to make sure that it performs as quickly as it can. The next thing we talked about, of course, is doing things in parallel. So in addition to using better tools, you might also have to think about how to make your software make better use of the time that it has to do things. Particularly if your software is I/O bound, if it's waiting on interactions across a network, for example, or waiting on interactions for the file system or those sorts of things. New features in Python that might not be in your LTS Linux distribution's version of Python, like async and await, could be a really huge win because it allows you to actually continue executing code while some other operation that hasn't completed yet is not completed yet. You can keep doing things. That's a huge win. If your software is primarily CPU bound, but the kind of work that it does is processing large data sets, and you can split those up into smaller pieces and do that work in parallel and then combine the results, which is called divide and conquer, then using multiprocess features in Python can be a way for you to do that. We're not going to spend today talking about all the ways you can make your software faster, but just getting you the idea that you can think about these things to make the time that your user perceives that the software takes shorter. And then finally, on the, what was the last bullet? Oh, do less work thing. So if you're building web applications, which lots of people are, and in Python you're probably doing that in Flask or Django or some other very popular Python framework, those are all pretty good about these things, but still, you have choices as to how requests are routed to your application. So for example, if you have been doing this for a long time and you're used to the old model of every time a request comes in, your program gets launched, from a time consumption point of view, that's terrible because you've got to go parse your configuration and open database connections and do all these other things every single time a request comes in, even though it's the same configuration for the last 10 million requests and the same database connections. Don't do that. Try to do all of that up front and share the results of all of those things between your instances. If you have a large application that has lots of requests coming in, then make use of the database connection pooling features that exist in your database libraries. And if you've never looked into it, and you're some person who is designing database schemas, denormalization in order to improve performance is something that you can absolutely do. There's lots of research papers and talks and blog posts and things about that. But it's the sort of thing you definitely do not want to do too early. Premature optimization can obviously be a very bad thing. But once you have identified particular queries or particular obstacles in your software that are taking a long time, restructuring the data so that you can reduce that time is something that can be a benefit too.
So the next form of time that we've been thinking about is time spent developing our software. I think a lot about this because I mostly work, or I spend almost all my time now writing developer tools. And I think for developer tools, speed is kind of the ultimate feature because when you have a tool that can be faster and faster, you shorten the iteration loop, and then that speed kind of compounds, right? If your tests take 0.1 second instead of 1 second, you become much faster to iterate. You can ship more quickly, try things more quickly. The other thing that I've observed, and we'll look at some examples of this, is that when tools are fast enough, they can kind of unlock like a step change in how you use them. So if something is really, really slow, and you have to run it on CI and you have to parallelize it over like 1,000 machines, you can no longer run that step locally. Maybe it's just like too slow to run locally. And if you actually build something that's fast enough to run locally, suddenly everyone on your team, and you included, can run, test, debug locally and get immediate feedback. I'm going to use the tools that we've worked on, so Ruff and UV, as two examples of tools that try and adhere to these philosophies. So Ruff is a Python linter and code formatter. So if you've used tools like Flake8 or isort or Black, Ruff can do a lot of the things that those tools can do. So it kind of analyzes your code ahead of time, tries to identify problems, and then suggests ways for you to fix them automatically. It's very, very fast. So it's like 10 to 100, maybe sometimes even like 1,000 times faster than some of the existing tools. And it's just grown a lot over the past year and a half, 2 years, to the point that it's been very well tested across a lot of very large projects. And one of the things that we saw, or that I guess I saw because it was just me working on it at the time, when I first released Ruff, and I was like, is anyone going to care about a faster linter? Like, is that, like, no one was coming around asking for a faster linter, at least in my life. It was just something that I wanted, and that's why I built it. But what I started seeing was stuff like this. So this is from Nick Schrock. He's one of the co-creators of GraphQL, and he runs a company called Dagster. They make a data orchestration framework. And for them, so they were running Pylint. It would take about 2.5 minutes to run over the largest package in their project. So their project consisted of a bunch of different packages, and just they couldn't actually run Pylint over the whole project at once. It had to run over each package individually because the project was too big. And over the largest project, it took about 2.5 minutes. So Ruff, meanwhile, could run over the entire code base in 400 milliseconds. So it's not just that you're getting feedback faster, but suddenly like you're actually going to run Ruff a lot more, right? Like you're actually going to engage with your tools a lot more when you're getting fast feedback.
One thing I'll warn you about, which Charlie knows about, for those of you who have adopted Ruff, it is so fast that there are times you feel like it didn't actually do anything.
Yeah.
And you have to go make changes in your code to force it to report an error to find out that, yes, it actually did run.
Yeah.
It's that fast.
That's kind of the new standard, I think, for at least
Yes.
for myself. It should be confusingly fast.
Yes, right. Yes.
So similarly, we built a tool called UV. It's a Python package installer and resolver. So if you've used tools like pip compile, virtualenv, probably everyone in this room has used those tools. They're incredibly popular. UV is designed to do very similar things. And again, it's a tool that we kind of built with performance in mind from the start. So trying to think about how can we make sure that when we ship this and we release this, that we're actually going to be capable of delivering something like a 10 or a 100x speed up over things that are being used today. We released UV in February, so it's been almost almost 90 days, I think. It's at about 7 million downloads per month, so it's been growing. And similarly, I think the thing that's amazing about performance is how it can change developer experience. So Armin Ronacher, who he was the original author of Flask and Jinja, he works at Sentry, and he wrote a blog post about UV when he released it, in part because he moved his project Rye over from pip tools to UV. And one of the motivations there was that instead of taking 5 seconds to sync a virtual environment, you can make it almost instant. And if like creating a virtual environment, installing your packages is instant, like suddenly you just have a totally different relationship to that act of like installing your packages and creating your virtual environment. So it saves you a ton of time and it really changes what it feels like to develop with the software. So, a couple things I would just call out about these things that we've built. One is concurrency and parallelism, like Ruff and UV use a lot of concurrency and parallelism. They're actually pretty different pieces of software. Like for Ruff, we don't actually use like async at all, but we can parallelize really heavily. So like every file is analyzed independently. For UV, it's mostly I/O, or it is doing a lot of I/O, right? It's like downloading stuff from the network, it's unzipping it, it's like moving files around. So there, everything's async, and we have like a very highly concurrent model. But in both cases, like that's a really big part of what makes them fast is having a very efficient model for how we pipeline and do different operations. The other is caching. This is important for Ruff, more important for UV. So in UV, we made a bunch of decisions to try and optimize for the hot loop of local development. So, often when you're installing a package on your machine, like you've probably installed it before, like for some other project, and you might have other projects on your machine that are also relying on that package. So we made a bunch of decisions to try and optimize for that case, which is you're often installing the same packages many times on a machine. And so that's one of the areas where UV shines the most is when you have, you're installing from what we would call a warm cache. So trying to make decisions in building the tooling that are optimized for local development. It's still very fast if you're not doing that, but like it's even faster if you are doing that. And the last piece here is, we built all this stuff in Rust. I think, for me, I don't know how applicable this will be to people in the audience, but part of what I view in terms of us building tools is we're trying to build a lot of fast foundational tooling to enable people who work with Python to not have to like think about some of this stuff and just get performance speedups for free.
Yeah, so Charlie mentioned before, we were talking about before about people who contribute to your projects. So if you go to the next slide, we've all seen, explosion of people contributing via public code repository platforms, GitHub, GitLab, Codeberg, all kinds of other things. And lots of first-time contributors too, right? People who come along, use your project, find some nit, find some little documentation thing or whatever, and they say, yeah, I can fix this. If their experience in trying to do that is poor, that means you're going to lose them as a contributor. They're not going to stay around with your project. So one of the goals you should have when you're setting all these things up is to make sure that experience goes as good as it possibly can. So moving on, if you would. Oh yeah, this was actually you.
Yeah, so this is actually the example that I was kind of hinting at before. This is again from the Dagster project. So originally when they were using Pylint, they would run a separate CI job for every Python package. So like every package would get a GitHub action workflow that would lint separately. And so over the course of the project, they had like hundreds of thousands of CI jobs that did nothing else but lint. And with Ruff, they could move everything to just like a local Git commit hook. So for contributors, right, they're getting immediate feedback rather than having to wait around for CI to spin up. And and the other effect here that was interesting was like the number of lint failures in CI obviously went down dramatically too, because if people can actually run that step locally, they're much less, like before people were kind of like pushing and then using CI as the way to get feedback on whether they were passing or not. If things can run locally, then they can get things working locally, push, much more likely to succeed.
Yep. I mean, how many of you have ever decided to take PyLint out of your pre-commit hooks because it was slowing you down too much? You don't have to do that anymore. So once you get beyond that point and you've optimized the process of creating the PR, then you want to also think about what the experience is going to be for the person who's watching that PR's tests and compilation and linting and all of those things run. So spending time to think about how you can best leverage the parallelism features of whatever platform you're using is very important, because it will get feedback to the contributor more quickly, especially when you have to test against a lot of versions of Python or dependencies or other things. For example, in one of my personal projects, it tests against 6 versions of Python and 5 versions of the service that it actually is designed to configure. So the matrix is very large. If the user had to wait for all those to be run sequentially, it would be probably 15 or 20 minutes, I think, before they got a green check mark on the CI output. But because they all run in parallel, it's about 1.5 minutes, probably, something like that. But the other thing you can do, which many people don't think about, is if your platform allows this, and not all of them do, if you can take one cell of that matrix and say, this is the one I want to test against first. Test this one first. Don't even start the other ones unless this one passes. And that's the one that's the most popular version of Python and the most well-supported version of whatever the other dependencies are, and maybe the most popular platform that you run on or something like that. Now, you can stop all of the other jobs from even running if that first one fails. If that first one fails because they forgot to run Ruff, or they forgot to do something else, or you're doing type checking and they forgot to annotate something or whatever, why waste all the time and resources for all those other jobs to run when they're just going to fail anyway? So those are the kinds of things you can think about to make that experience better for the people contributing to your projects.
Similarly, you can think about how do you cache things in CI. So, one of the ways that we've been trying to hammer home around making things faster is doing less work. So, for example, in UV, Heineck created this setup cached UV GitHub action, which essentially takes the UV cache, stores it in GitHub Actions, and restores it when you run. So it lets you carry over the cache created from job to job when you're performing GitHub Actions, installs in GitHub Actions. And it's a good demonstration of how doing less work can make everything better. It speeds up your CI. It ensures that you have more consistency across runs too.
Yep. So let's see, we're going to alternate this one, right? I think the first one's yours.
I think this is me.
Yep.
Yeah. So the last piece here, which sort of coincides with all of them in some different way, is thinking about how do you reduce the amount of resources that you're consuming, both when you develop software and in the software that you deploy. And this is a win for everyone, right? It can save you cost. It saves the world compute. Sometimes there are quick, easy wins here, and sometimes it will require some work from you to restructure your project, change the tools that you use, et cetera, et cetera. I'm going to talk through just a couple examples of how we've seen this play out. So one is from Home Assistant. This is a really popular GitHub project. They have almost 70,000 stars. I think they have 4,000 contributors. It's an open source home automation framework. So it's sort of like software to program, a Raspberry Pi and similar devices, and they have a bunch of integrations for programming your garage door and stuff like that. So they moved over to UV for dependency management, and they were able to save about 5 hours of execution time per build. So it's 215 hours per month. And the whole release pipeline went from 2.5 hours to 20 minutes. So it's the wins here, it's not just about developer experience. They were also able to dramatically reduce just the amount of compute that they were using per build.
Right, and thinking in mind that's not just time watching a clock. It's computers in somebody's data center just thinking and thinking and thinking and thinking for 2.5 hours instead of 20 minutes. That's gigantic.
Yeah, we saw a similar thing with Airflow. So Airflow very popular data orchestration framework. They moved to UV for dependency management. So their canary builds went from 12 minutes to 4 minutes. Production builds went from like 4.5 minutes to 2 minutes. And the constraint solving step went from 5 minutes to 30 seconds. So again, like they're running this stuff constantly, like all the time. And by choosing to use different tools, not only can you make things a lot faster, which will improve developer experience, but it can also reduce the total amount of resources that you're actually consuming and using in your project.
Yep.
So a couple things I think about here. So one, fast software can also be efficient software. Like we didn't just make those things faster by parallelizing the jobs massively or something like that. We actually wrote more efficient software, so it got the job done faster and using less compute. Saving developer time can also save compute resources. So in all of those examples, we were reducing the feedback loop and the iteration loop for those teams, but they were also massively saving the amount of compute resources that they were using. And then the other, which I try to have kind of a unique, naive view here, which is like performance doesn't always have to be a compromise. Software can be optimized without sacrificing features or correctness. I think when we started working on a package manager, I think I heard a lot of opinions like pip is I/O bound, so like it can't be optimized. And I hope that we've proven that isn't true. But a big part of what we're trying to do is just force people to think about how much faster things can be, hopefully in a sort of methodological and rigorous way.
Yep. So I mentioned earlier, we've talked a lot about how parallelism can be a win. Parallelism can actually be a very bad thing in CI if you don't do it well. A lot of CI platforms, for example, will launch an entire virtual machine for each job that runs in your matrix of jobs to run. Launching a virtual machine is a very resource-intensive thing to do. Obviously, a kernel has to be started, and a user space has to be started, and all of these kinds of things. So you have to think about exactly how you're applying parallelism in your CI to make sure that you don't get better wall clock time at the expense of compute resources. If you can somehow find a balance between those two, then everybody wins. So one example that I like to use is if you can find a way to use containers instead of virtual machines, that reduces resource consumption substantially because a container doesn't have a kernel and a user space to start and all of those other things. It's just a virtual environment of a type, not a Python virtual environment, but a different type of virtual environment. So they're much quicker to start, quicker to tear down, and that obviously then saves compute time. If you can also build your own container image, which has all of your dependencies and everything already in it, that goes back to the caching idea, right? Doing less work. If the container starts up and everything that it needs is already there, and then the source code it's supposed to test has been injected into the container, it can just start. It doesn't have to wait to install packages and build virtual environments and all of those kinds of things. This has another pleasant side effect, which is this is something that I do in my own projects, which is how many of you have pushed a PR up to whatever platform you use, it fails, and you look at the failure log and you go, I cannot figure out why that failed. I have no idea why that failed. Yeah, we've all been there. And what do you end up doing? You make a little change in the branch, and you push, and you wait for the job to run again, and it still fails. And then you make another little change, and eventually you finally figure out what it is. The reason you have to do that is because you can't replicate that environment on your local machine exactly the way it is in the CI environment, so you have no choice. But if you've built everything as a custom container image, you can just pull that container image down to your machine and run the exact same tests in literally the same environment that they're running at in the CI platform, saving you time as well then, because you can get to that resolution process much faster. For example, if finding the reason that it fails means you need to actually launch a debugger and intercept something that's happening inside the software, you can't do that in a CI platform, but you can certainly do that locally. So those are really big benefits as well. And then if your CI platform will let you do this, not all of them will, if you've got a bunch of things to test against, if you can test them all inside one container instead of launching a container for each one, that's again reducing the work. If all of the dependencies are already there, again, you go back to that project that I mentioned that tests a bunch of versions of Python and a bunch of versions of another service. As you can imagine, the container image for that one's somewhat large. I think compressed, it's like 650 megabytes. no, excuse me, it's large anyway.
650 gigabytes.
It's very large. But the result is I only have to pay the cost of downloading it once. Once it's downloaded, then all of the jobs can use that and everything is done and I don't have to build all of those things. So those are things that now we're talking about. You have to put a little more of your software engineering brain to work to figure out how can I optimize this process, making choices that aren't going to be a burden for me to maintain in the future, but also end up making the process faster and using less resources.
All right, so here's a cool example, and you'll be glad to know this has absolutely nothing to do with anything that I built. This is again from Home Assistant. So Home Assistant, right? I mentioned it's a home automation platform. So they have like a core, which is like the core SDK, and then they have a bunch of different integrations. And when someone makes a change to Home Assistant, they want to figure out like what tests do we actually need to run for this change. Like, do we need to run did they change something in the core? If so, we need to test the core. Maybe we need to test a bunch of the integrations. Did they change like just one of the integrations? If so, maybe we just test that. So they changed the structure of their CI such that initially they would kind of distribute the work. They would pass it out to a bunch of different jobs, and each of those jobs would run that test discovery process. And all they did was they inverted it. So they started by doing the test discovery process on one machine, and then they told each of the individual jobs which tests they had to run. So rather than like spinning up 10 machines and having them all do test discovery, they did test discovery up front and then told the machines which tests they had to run. So the only thing that they changed was like they stopped doing that test discovery on every single machine. And it saved like a huge amount of time. Like if you look back at all the pull request activity, in March 2024, it's like 168 days. You computed these, so hopefully that's right.
No, they did, but
I
copied it. Think about that, 168 days of compute time in 1 month. That's 5 months of compute time consumed in 1 month that now won't be consumed anymore.
But the interesting thing about this example is it doesn't actually change the wall time. Like
right.
the time from when you push to when you get feedback didn't actually change. Because sequentially, all those steps are still running. Like you still have to do test discovery, and before they were just doing it all in parallel. So the actual wall time didn't change. This didn't actually improve, maybe marginally, but like in theory, it shouldn't really measurably change the time it takes from when you push a PR to when you get feedback. But they got rid of that huge fan out of repeating all the work on every single machine, of doing the test discovery on every single machine. They're still doing the test discovery, right? And that still has to happen. But now they do it once instead of doing it like, a bunch of times. And this kind of goes to show like you should be thinking about work that's orthogonal, right? And like work that's being repeated across those different machines. How can you restructure your job so that you're doing, if something is going to be a bottleneck, it's going to be done at a bunch of times, like can you do it once and figure out how to reorient the pipeline?
Yep. So then another aspect of CI, especially for public CI, and this is very relevant for us here because Fastly actually serves you all of the content from PyPI, which is why we're here as a sponsor. I just randomly picked a day from last week and did a quick check, and on that day, PyPI delivered approximately 1.4 billion package downloads. And if you've never looked at the statistics for PyPI before, that number may shock you. That's kind of normal. That's not especially high. That's just a random day. Obviously, it varies. Weekends tend to be lower than weekdays and things like that, but that's not an especially high number. It's extremely safe to say, and I think there was a video, did they just do a video thing, the PSF people, last week? They talked about how Fastly sits in front of PyPI, and you can imagine, would you want to have to run a service platform that could serve that many downloads in a day all on your own, and more importantly, have to pay for the bandwidth to serve that many downloads? Nobody in this room should be raising their hand, by the way. That would be a terrible choice on your part. This is why we have CDNs to offload these kinds of things, and in particular, Fastly has a particular relationship with PyPI that makes it work especially well for them. But moving on from that, starting in late February, the data that's logged for PyPI downloads now has a flag to indicate whether that was detected as being a download that was coming from a CI platform or not. It's certainly not 100% accurate, but it's reasonably good, and it's enough to do a quick analysis, and so I did. 386 million downloads of packages happened in one day from CI platforms around the world. That number alone a few years ago would have been a gigantic number of downloads for a package repository. Now it's just, whatever. But think about it. If all of these things that we have been talking about, caching, pre-building container images, doing less work, all of those kinds of things, if the Home Assistant example that Charlie talked about had actually involved downloading packages on 10 machines instead of doing it on one machine, that 386 million number could drop a lot. Like it might drop 90% if all of these techniques were applied in all of these big projects around the world. That saves bandwidth and lots of other things, which are also resources that we have to think about. Delivering data around the internet is not a zero-cost operation, so we have to think about those things too. So, hopefully, we've inspired you to think about this problem in a way that you haven't thought about it before. That sometimes it's really easy. You just switch tools. You can say, I'm going to switch over to this other tool. It's so much faster and everybody wins. Great. That's good for everybody. Your process gets faster. Your contributor process gets faster. Fewer resources get consumed. Sometimes you need to think about it a little more and say, okay, well, maybe I should spend an hour, maybe it's an hour, and go look at the various parts of my CI workflow to figure out what could be done better. And if I can find something that could be done better, and I invest an hour, or maybe 2, in fixing that, and it turns out that every time my CI job runs, it takes 10 minutes less than it used to take, well, that's a pretty good ROI, right? You put 2 hours in, and in a couple of days, it's already been returned back, and now it's going to be returned back forever because you're going to continue with that optimization in place. So find something in your CI workflows or your developer workflows where there's work that's being duplicated that doesn't need to be, or caching that could be done where it's not currently cached, or just inefficient usage of resources, and say, yep, I'm going to actually fix that. Not just add a new feature in my software or fix a bug, but I'm going to go fix that. And with that, this is our goal, right? We don't want footprints all over the internet every time your job runs. We would like to be able to see your job ran. You can still see it. I mean, it's not going to, running a job in a CI platform is not invisible. It's not transparent. It's going to have effects. We just want those effects to be as small as they can possibly be. And with that, I think we're ready for questions. Yep, we are. Thank you all. And I think, do we need the mic for questions? Okay,
Yeah.
we do need the mic for questions. Do you want to, if people raise their hands, are you willing to go out?
I'm
Okay.
willing to go out.
All right. In this unruly crowd. Anybody have a question?
Do you want a question? Oh, sure.
Well, but then if he has to answer, he has to be with you. So, but I don't see any hands. Nobody has any questions. Oh, there's, of course, way in the back.
Okay, wait. Maybe I'll do this one first. That's okay, just because it's closer.
Do you remember kind of what project you were working on when you were sitting there being like, God, I would kill someone if I could get like a faster linter right now?
Yeah, I was working on, it was at my last job. I was working on a computational biology company, and so we, there were kind of 2 of us that were responsible for all the software infrastructure. Our technical team was like between 8 and 10. So most of the people on that team were like data scientists and machine learning researchers, and there were 2 of us who were building all the software infrastructure. So, we were using Python because we were doing scientific computing, and we were just trying to figure out how to get as much leverage as we could out of having 2 people maintaining a really big software stack, which meant a lot of tooling. So like, we had MyPy with all the strictest settings. We just had a really like tooling heavy process. And the company as a whole was like between 20 and 30 people. Our code base was probably like over 250,000, but probably under like 500,000 lines of code. So it was like a big project, but like by my standards for a company of that size, but not by, there are certainly much bigger projects out there. And so for me, part of that was, if I'm spending all this time investing in the tools and kind of struggling with the tools, like I can only imagine what even bigger projects are having to kind of fight through.
Yep. You one in the back there, I
I'm
think?
going to go all the way to the back first. It's fine, don't worry.
Yeah, I was just wondering if you had any particular observability patterns you do to kind of justify some of these changes. I mean, you can always justify improving and improving time in CI, but do you have it's often it can be hard to kind of justify with real numbers and say, oh, this will be faster, but how much faster, and where do you focus first, and so on?
I don't know that we do. I haven't actually seen, like, for example, academic research and other people publishing about, like, analyzing the effects your CI workflows have. It's certainly an area that a lot of people could spend time doing that if they wanted to. I hadn't even seen any blog posts from large projects until these two from the Home Assistant project about people focusing their time on just making performance improvements there. So I suspect what that means, it's a kind of a new area for people to be thinking about. 10 years ago, possibly even less than 10 years ago, these were not things that crossed anybody's minds. We did not have gigantic, free as in beer, but not actually free, compute platforms doing all of this stuff for us. And so as they grew as rapidly as they did, people just say, well, it's free, so I don't have to think about this. And then we start to hear news stories about, you know, in this particular case, if we're going to talk about GitHub, the compute resources all come from Azure, which is Microsoft's cloud. And so every time you hear that Microsoft's built 4 new data centers, it's like, and the news stories are about how much power that's going to consume and how much water that's going to consume. And you think, wait a minute, some percentage of the reason that they needed to build that new data center is all of these jobs are running in GitHub Actions. If we could actually reduce the number of work, the amount of work being done in GitHub Actions, who knows? Maybe they can just say, well, actually, we don't need 4 data centers, we need 3. That's huge if we can accomplish something like that. But it's kind of a new thing for people to think about because we didn't have these giant shared compute resources like this even 5 or 6 years ago.
I think, I mean, maybe another, you sort of touched on it, and so maybe I'll just take the opportunity to talk about it. Like, I sometimes think about in performance work, like similar to other things, like building an MVP. So like, if I have some theory about, well, first of all, like, for us at least, like anything that we work on, ideally it starts by showing up somewhere in a trace. So we do some profiling, or we kind of notice something slow. We see some method that's showing up more than we think it should, and then we start looking into it. And then, you know, for me at least, I think a lot about like, what's my hypothesis for like why and how this could be faster, and like how can I prove that as quickly as possible, even if I'm not writing production-ready code. And you do that all the time with like building features and stuff, right? Like, is this a way that this could work? I think it's similar, but a little bit different with performance, because you need to be thinking about, as I simplify and reduce the problem, like what am I removing that is actually important for measuring performance differences. So, you know, we shipped like in Ruff, we shipped a new parser recently, and like the first, you know, I would say like a huge portion of the work was going from like the MVP to actually production. Like that was like several months probably. But like the work to prove that it was faster, I mean, that was also a lot of work, but it was a lot less than the work to go to production. So just thinking about how can you like define what your hypothesis is for how this thing could be faster, and then isolate it, test it, and do the least amount of work possible to figure out whether it's actually true or not.
Yep. Scientific method applies here too. Yeah. There was another one over here?
Yeah.
Yep.
Sorry,
Hey, thank you so much. We use Ruff a lot in Rapids, and also, you know, I worked with you recently on getting many Linux tag support in UV. Oh, nice. Yeah. So I'm interested in your take on, do you think there's room for tooling to be more opinionated on kind of that last bullet point that you said about doing less work? I've used PyUpgrade, which sometimes has like, it'll replace micro patterns in your code that maybe can offer small amounts of performance benefit. Do you think there's room for tooling to be more opinionated on doing things like things that you would choose between pattern A or pattern B by micro benchmarking or things like that?
Yeah, totally. So we do some of this in Ruff. Like we have some rules that are oriented around like you're doing something in a way that's not incorrect, but we kind of identify that there's a pattern here, and there are like slightly faster ways to write this. I think it's good. I think it depends. Like not every project I think should care about that, which is maybe a weird opinion coming from me as someone who works on like high performance tooling. I think I actually want Ruff to be doing more of that, but it needs to be a lot better. Like we need to make tools that can analyze Python code with a lot more confidence and detect like higher level patterns. Like we do, we do some things in Ruff right now, but it's pretty limited in terms of the static analysis that we can do. So it's something that that's like going to be a big push for us starting like maybe 2 months ago till the end of the year, is like trying to make it much higher confidence, being able to do like type inference and other kinds of analysis on Python code to enable transforms like that. But I think Python is it's a hard language to analyze with high confidence because it's so dynamic, and that's one of the strengths of the language. And so it'll always be a little bit of a challenge, but I think the more that you can offer people suggestions like that in a way that doesn't require work from them and also teaches them something, like that's a big part of what we want Ruff to be, is like we're not just making arbitrary changes to your code, like hopefully we're also teaching you something about why.
Yeah. And there's certainly plenty of evidence for the thing you're talking about in other language ecosystems. In Rust, you have Clippy. In Go, you've got other tools. There's static check and others. In C++ land, there's the Clang tidy tools and other things which do similar sorts of things. They will detect certain patterns, which either there are more performant alternatives to those, or if you've upgraded the Rust edition or the version of Go you're using or the version of C++ you're targeting or whatever, there are just better ways to accomplish the same end. It's interesting to me as I experience all these tools, some of them are, they'll just tell you, and others, like, they just change it. Like, that's the first time I used Ruff to do those things, just changed it. And I thought, do I really want a tool doing that for me? And then after like the fourth or fifth time, I thought, I didn't have to open an editor or do anything. It just did it for me. Yeah, great. That's fantastic. Thank you. So look, if your tests still pass and you feel you've got pretty good test coverage, and the tool made this change because it has an opinion that it thinks it's better, that's fine for me. I'm fine. We all, in the Python world, we all experienced that with Black for the first time, right? It was the first really highly opinionated tool in the Python ecosystem. And people were like, but it's just going to change the format. And all of us that have been around open source forever said, how many hours have we all wasted fighting over code formatting decisions in open source projects? We don't do that anymore. Everybody just uses Black and that's it. And we all dislike aspects of the choices that it makes, but we don't have to discuss it anymore. It's just what it is. So there's definitely room for tools to have really strong opinions about things, as long as there's something, even if it is literally just opinion, there's still some rationale that's there to document why it made that choice. And if it's arbitrary, then people will fight against it, but yeah. Anybody else? Oh, one more. I think we have, how much time do we have? Yeah, we got time for one more.
Sorry, my voice is a little rough, but I really like Ruff a lot. It's a fantastic tool. I'm wondering, why did you choose to implement it in Rust? Is it just raw performance, or is the concurrency model not something you could implement in Python?
Okay, so I think there were like a couple different reasons I did it in Rust. Maybe 3 reasons I can think of. Okay, so the first is that this one's sort of embarrassing, or I don't know about embarrassing, but like I just wanted to get better at Rust and learn Rust. And so when I started working on Ruff, partly it was like, I feel like I need to learn Rust, and for me at least, to learn Rust, I think I need to build something from scratch, and this is a project I want to do, and so I'm going to do it in Rust, and I'm going to do it that way. The second was I'd started to see Rust-Python interoperability in my previous job. So with Py03, there's this whole ecosystem around building modules in Rust that you can then expose as Python functions effectively. And so I'd seen there was kind of this nascent community that was really focused on how can Rust and Python be used together. And that to me was really impressive. So the fact that I could take a project like Ruff, package it as a Python wheel, and then people could pip install it without having to install Rust was really appealing. So in terms of using a language that wasn't Python and was more like systems oriented, it made a lot of sense to me. And the third was part of what I wanted to do, or part of the like hypothesis behind Ruff and why I started working on it, was I was seeing a lot of the things that were happening in the web ecosystem, where more and more tooling was being written in not JavaScript. So like they were starting to write bundlers first in Go, and then there was a lot of work in Rust, and now in Zig. So like in the web ecosystem, they're just running a lot of tools locally, and they always have been, because they have like transpilation, minification, bundling. They have all these steps that are required to get to the application. And that led to a lot of people investing in performance and trying to use languages other than JavaScript to eke out more performance. So part of Ruff for me was asking, like, could we do the similar thing in Python? Like, how different would it be if I could build the linter in Rust, and where would I see performance gains? Yeah, I think you could probably build faster linters written in Python than the ones that exist today. Like, I'm sure you could make faster ones. I don't know if you could write a Python linter in Python that will be as fast as like the fastest Python linter you could write in Rust, if that makes sense. I think the floors or ceilings, however you want to look at it, for performance are different. But whichever language you're using, there's definitely room for optimization. I'm actually giving a talk tomorrow about Ruff that'll be really focused on like just the question of how, like, what makes Ruff fast. And some of the lessons there, I think, apply to, like, it's not just about Rust. Like, I think there are other lessons there that will apply to other languages. But that will go into this in a little more. I don't want to spoil too many of the talking points for that talk. We'll go into it in a little more detail.
All right, we have room for one more, I think. If not, all right, thank you all for coming. Appreciate it.